This is the video for the Pre-Calc Unit 9 Lesson 2 notes. And I will be going through the answer key for these notes. And the first thing that I want to talk about in this lesson is limits that are involving infinity. So either when we talk about the x value approaching infinity, or if we are talking about the answer or the y value approaching infinity. And so if the x values are approaching infinity, and in fact, if you look at the notation here, x approaches infinity or x approaches negative infinity, that should be familiar to you from Algebra 2 when we were talking about end behavior. And that's the vocabulary that we used in Algebra 2. So when you're talking about taking the x value to positive or negative infinity, you're basically looking at the end behavior of the function. And your answer is going to either be up or down, positive infinity or negative infinity, or a horizontal asymptote, which would be a number. So if the question is the limit as x goes to infinity or x goes to negative infinity, and your answer is a number, which we'll look at an example of in a minute, then that indicates that you have a horizontal asymptote. And that's what this means right here. If y equals c is a horizontal asymptote, if you get a number for your limit value. If I give you a problem where the limit goes to a number, where x goes to a number, when I give you a limit problem, and I say x goes to 5 or x goes to negative 5, and it's not infinity or negative infinity, but your answer for the limit is infinity, then that indicates that you have a vertical asymptote. So there's two different situations, and it has to do with both how the question is asked, meaning what x values am I asking you to go to, and how the limit is answered. And that, remember that the limit represents a y value, and one of those two things is going to be infinity, and that'll let you know that it's either a horizontal or vertical asymptote. So let's take a look at this first example. So in this first equation, I'm asking you to find the limit as x goes to infinity, and remember that that's just asking for the end behavior on the right. As x goes to positive infinity, that's on the right end of the graph, and you're talking about the end behavior of that graph on the right. Now, the tables that we've been doing have always had a value in the middle of the table because we've been going to x equals or x approaches a number, and we want to approach that number from both the left and from the right. But positive infinity is the farthest right number. I should turn off all my notifications when I do these videos because I was just distracted. My apologies. So positive infinity is the farthest right number that exists. You can't approach it from the right. You can only approach it from the left. So when we make our table for positive infinity, what we're going to do is we're going to put that positive infinity all the way down here because that's the only place it can go on a number line. And we're going to approach it only from the left. And when we fill in the table, it's not going to be all these decimal places to the tenths and hundredths and thousandths. What we're going to do is we're going to start with some smaller numbers and then get into bigger numbers and bigger numbers to approximate infinity. So I'm going to start with a couple of one-digit numbers like 1, and then 5, and then maybe get into some two-digit numbers like 10 and 25, and then maybe grab a three-digit number like 100, and then maybe a four-digit number like 1,000. And in that way, look and see what is happening to the y values as the x values get bigger and bigger and bigger. So as I did in the last video, what I want you to do is pause the video in a minute. Actually, for those of you that didn't watch the other videos, let me talk you through the calculator steps. But I want you to pause the video, get the y values yourself, and then come back and check your answers, because I'm not going to run the video while I'm filling in the y values. But just in case you don't know those calculator steps, over here in the margin, let me say that first of all, you want to just clear your calculator. So do second plus sign and then 7, 1, 2. And then you want to go to y equals and type the expression. So you want to go over here and grab this expression, and you want to type that into the y equals. Type it as a fraction, use parentheses and the exponent and everything else. And then you're not necessarily going to look at the graph. I mean, you can, to give you a feel for what the graph looks like, and in a minute we're gonna actually draw the graph. But what you want to do, if you were to press second table or second graph, which will give you the table, you'll notice that the only x values are integers. And if you wanted to use decimal values, you couldn't find x as decimal values. But here, the other issue is that you would have to scroll a very long time to find x is 1,000. There's a much faster way to do that. So to change the x values in the table, or to change the table itself so that you are only looking at the x values that you want, what you want to do is press second and then window, which brings you to the table settings. It actually says TBLSET above the window button. So you want second window. And when you do that, you'll see that if you arrow down a couple of times, it says INDPNT. That's independent. And you want to change that to the word ask. So it's just a toggle. So you put your cursor over the word ask and press enter. Now when you go to second table or second graph, which takes you to the table should be empty of any x or y values. And then you can type in these numbers here and just type 1, hit enter, type 5, hit enter, type 10, hit enter, and you're entering the x values, and the calculator will spit out the y values. So why don't you go ahead and pause the video and come back in a minute, and I will have the x value or the y values for these x values. So here's what you should see for your y values. Just notice that for the first 5 of them, the numerator stays 1 and the denominator continues to get bigger and bigger. So if you have a fraction where the denominator outpaces the numerator as far as the value of it increasing, you're going to be getting closer and closer to 0 without ever actually equaling 0. And in this last one, the calculator couldn't even handle the size of the denominator of the fraction, and so your calculator automatically switched over to decimals. And that E-6 thing just means that it's moving the decimal point over 6 places. So it's going to be 0.5 zeros and then a 1. And it's just going to continually get closer and closer and closer to 0. And so that means that as you have your x values approaching infinity, your y values are approaching 0. So your answer to the limit here is 0. And what I want to do then for sketching the curve is you can change your table set back to auto. And when you're in that, and that's all the stuff that I did over here. So if you go back and change the table settings to independent auto, it'll go back to giving you x values that are integers. So now I'm going to sketch this, and when you look at the graph, hopefully you can see, and it makes sense to you algebraically, that there's going to be a horizontal asymptote at y equals 0. And that's what we're saying here, is that because we were looking for the end behavior as x goes to infinity, and it goes to a number, that number is going to be your horizontal asymptote. So you've just basically proven that there's a horizontal asymptote for this function at y equals 0. There's also, and again, algebraically, I hope it makes sense to you from the equation, the x minus 2 aspect of the equation, that there's going to be a vertical asymptote here at x equals positive 2. And what you can't see is me turning the iPad in all kinds of weird directions in order to be able to draw these graphs accurately, or semi-accurately, or hopefully a little bit accurately. Anyway, you don't need to graph a whole lot of points. There's a point at 1, 1, and there's a point at 3, 1. And then the graph approaches the horizontal asymptote like this here, and on the other side as well, like that. And then the graph approaches the vertical asymptote like this. And you can see that in the graph screen on your calculator. And there you have a sketch, a rough, very rough sketch of the graph of that function. Number 2 is asking you to find the end behavior, excuse me, of this expression, but is on the left. So this time we're looking for the limit as x goes to negative infinity. That means the left. Don't miss the negative in the function. Okay, this function is negative, and then 3 over x squared plus 2. Okay, so when you type this into your calculator, that's what you're going to put. Now, because we're looking for the limit as it goes to negative infinity, and negative infinity is the farthest left number, or the very smallest number on the number line, you cannot approach it from the left. You can only approach it from the right. So when I draw my table, I'm going to put negative infinity as the farthest left number, and I'm going to be approaching it from the right. And so I'm going to fill in my numbers, and again, I'm going to use smaller numbers and then grow to bigger numbers. And I'm going to start over on the right with the smaller negative numbers, like negative 5, and then maybe negative 10, and then I'm just going to keep getting bigger, negative 25, negative 50, and then how about negative 100, and then negative 1,000, and just see what's happening with the y values as the x values continue to get more and more negative. And I'm actually going to type them into my calculator, starting at this end and going toward that end. It's just easier for my brain to process the values in order of in the table in the way that they are on the number line. Type them in however you want, really. You can go in whatever order you want, and then come back in a minute and fill in the y values on the table. So pause the video, fill in your y values, and then come back and check your answers. So here are the y values that you should get. And when you look at this table, then what you should see is that as x approaches negative infinity from the right, the y values approach positive 2. So what we're saying here is that the limit as x approaches negative infinity is equal to 2. And remember that limits approaching positive or negative infinity are talking about the end behavior. So we're saying here that the limit as x goes to negative infinity, or the end behavior on the left, is equal to 2. And whenever our end behavior equals a number and not a positive or negative infinity, then that means that there's a horizontal asymptote. So this function has a horizontal asymptote at y equals 2. And if you look at that on the graph in your calculator, you should see that graph appears to have a horizontal asymptote at y equals 2. So let's go ahead and draw the graph. So I'm going to put that horizontal asymptote at y equals 2. This graph also happens to have a vertical asymptote at x equals 0. And then I'm going to change my calculator back to the independent auto in order to look at the actual numbers that I might want to graph. And what you should see is that when you look at the graph in your calculator screen is that it's symmetric about the y-axis. And so what I would just do is graph the numbers on one side of the function and then just mirror those values on the other side of the function. And excuse me, so at -3, let me start there, and I'm just going to put just a few points to give me a rough idea, but at -3, the y value is 5/3, so that's about 1 2/3, so that would be about there. And at -1, it's -1, and that should give me the general shape. If I wanted the -2 5/4, that would be about there. And that gives me the general shape of the graph, and then I can just mirror those points over here. Something like that. And then the graph gets closer to the asymptote here and here. And then on the other side, I'm getting closer to the asymptote here and here. All right. So this page says that the problems in this section are about limits involving infinity. And clearly here I'm asking you to find a limit as x approaches a number. So your answer for 3 and also for 4 are going to have something to do with infinity because the question doesn't involve infinity. So your answer is going to involve infinity. Having said that, what I want you to keep in the back of your mind as we're working through number 3 and number 4 is that we're computing limits that will end up showing us that we have a vertical asymptote. As x approaches the number from the right and from the left, if your answers go to infinity, that implies or that indicates a vertical asymptote. So go ahead and type the function here into your calculator. Use the fraction function in your calculator, alpha y equals enter, to type it as a fraction. Make sure that your table settings are changed to ask for the independent variable. And since we're looking at x approaching 3, we want to put that 3 in the middle of our table because we want to approach 3 from the left and from the right. And so the numbers that you're going to use are the same as the numbers that we used from lesson 1 when we're approaching a number from the left and the right. I want to think, what's 1/10 less than 3? Well, that would be 2.9. What's 1/10 more than 3? That would be 3.1. Remember that if we're dealing with negative numbers, you have to stop and think because everything's backwards. But here then on the left, if it's 0.9, then we're just going to keep including more 9s, so 2.99 and 2.999. And if it's something 0.1, we're going to start including some zeros, so 3.01 and 3.001. And so what I'd like you to do is pause your video and go ahead and type all of those numbers into the X column in your table, and write down your Y values, and then restart the video, and we'll talk about what the limit is from there. So what you should see here is that the numbers on the left are getting more and more negative, and the numbers from the right are getting more and more positive. So the numbers from the left are approaching negative infinity, and the numbers from the right are approaching positive infinity. And so first of all, they're not approaching the same thing. And second of all, remember that infinity is not a number. And so here we're going to say that the limit does not exist. And then we're going to remember that we're going to give a reason for that, and we're going to say that the function does not converge to a value. Goes to both positive and negative infinity. And the other thing that we had just said was that if I have you looking for x approaching a number, and your answer is positive and or negative infinity, that indicates that there is an asymptote, a vertical asymptote at that x value. So before I even look at the graph in the calculator, I know that there is a vertical asymptote at x equals 3. And so I'm just going to go ahead and draw that asymptote at x equals 3. Now, based on the algebra, you know that the degree of the numerator is the same as the degree of the denominator, and the leading coefficients are 2 over 1. And so there's going to be a horizontal asymptote at y equals 2. And then we're going to graph some points. So I went ahead and changed my table settings back to auto so that I can look at whole number x values. And when I'm graphing points here, I see that it's pretty easy to graph -4, 1, and then just to get kind of a feel for what else I can graph -2 3/5, which is about there. At 0, it's -1/3, so it's about there. And are there any other values that are fairly easy to graph? Oh yeah, 2, -5 is way down there. So maybe partway in between. 1 is -3/2. So that's about -1.5. That gives me a good idea of the points on the bottom left. So let me graph that curve. And then on the other side of that asymptote, I can graph 4, 9. Oh, no, I can't graph 4, 9 because that's off the top of the graph. 5 would be 11/2, and that's just 5.5. So at 5, I'm going to graph 5.5. And 4 would be 9. That would be way up here. So that gives me just a feel for where that would be. And then at 10, it's 3, but I don't even have to 6, 7, 8, 9, 10. So it would be like maybe here. Let's put 1 or 2 more points. So 8 is 17 over 5. So that would be 5 2/5. So 5, 6. That's not right. That would be 3 2/5. Sorry. So at 8, it would be 3 2/5. 1, 2, 3 2/5, right about there. That makes way more sense. That's sufficient. That gives me enough points to kind of get an idea of what this graph is going to look like there. and then going toward the asymptote out there. So your graph should look less like that, hopefully better than what I just drew, but you get the idea. And then in this last problem, again, you had the hint that your answer is going to be positive or negative infinity. And on the test, I won't tell you. This problem is just going to be mixed in with all the other problems. So if I say to you, find the limit as x approaches a number, your answer may be a number or it may be in infinity, and you're going to need to discern that. Remember that if your answer is infinity, that implies a vertical asymptote. So let's take a look at this one. We're looking at x approaching -2, and so I want to put -2 in the middle of my table. So I want to be approaching -2 from the left and from the right. And again, be real careful when the x values are negative. They're going to be a little bit backwards of what you think. And so the number that's 1/10 less than -2, or -2 minus 1/10 is going to be -2.1. And then the number on the other end of the table that is 1/10 to the right of -2, or -2 plus 1/10, is going to be -1.9. And just sit back for a second and make sure that that makes sense to you as far as how number lines are set up, and that the negative numbers work somewhat backwards from the positive numbers. Get all that in your head. And then remember that if it's 0.1, we're going to throw some zeros in there, so it'll be -2.01, -2.001, and then -1.9 when it's 0.9, so you're just going to bring in extra 9, so 1.99 and -1.999. So go ahead and pause the video. Make sure you get this function typed into your calculator. Make sure you change the table set to independent ask, and then fill in the y values. Pause the video and come back when you've got your y values filled in. So here's the y values that you should have computed in your calculator, and this time both sides, both the left and the right, are approaching the same-ish number, but it's not really a number. They're both going the same place, I guess, is a better way to describe it. Unlike number 3, in number 3, remember, the one side was going to negative infinity and the other side was going to positive infinity. But here, both sides are going toward negative infinity. They're just getting hugely negative, huger and huger. And if you put a few more 9s in there, you just get ridiculously huge. But remember that negative infinity is not a number. This limit does not exist. And again, it's because the values, the f of x doesn't converge to a value of f of x. And again, because we said that x is going to a number and the limit ends up going to infinity, we've got a vertical asymptote. And so we're going to draw a vertical asymptote at that number. X is -2. And then remember that algebraically, the denominator has a bigger degree than the numerator, and so there's going to be a horizontal asymptote at y equals 0. Let's label our asymptotes. Y equals 0, and x equals -2. And again, I'm going to put some points here. So on the left, and this graph is a little tricky to draw, so on the left of the asymptote, it should look something like this. And don't spend too much time stressing about this graph on the right, because it kind of crosses over that horizontal asymptote and comes back down underneath it. But I'm going to graph the points that I can graph, so I can put, for example, -1, and 0, 0. Don't get freaked out that you're touching the horizontal asymptote. Remember that horizontal asymptotes can be crossed, and the horizontal asymptote is only about the end behavior and not about what happens in the middle. Then as you go past 0 to the other positive numbers, it's going to go up slightly and then it's going to come back down, but it's going to be above the horizontal asymptote then, and getting closer to it from above. And that's actually a concept that you'll study in calculus, is whether you're above or below an asymptote. And if we had time this year, it's not a difficult concept, it's just we don't have time, but if we had time this year, we could study that as well, the behavior of a function around an asymptote. So there's your answer for number 4. And again, that indicates a vertical asymptote. 3 and 4 are about vertical asymptotes, and 1 and 2 are about horizontal asymptotes. So on this page, what I think that you're going to find yourself feeling is that we've kind of already talked about this. So the only thing that's truly new to you on this page is the notation. And we have been referencing all along the limit as x approaches a number from the left and the limit as x approaches a number from the right. And so what we're going to do is we're actually going to separate those two ideas and sometimes only talk about the limit on the left or the limit on the right. And so we're going to talk about the left-hand limit, and the notation for the left-hand limit includes this little negative sign. And it's kind of like where an exponent would be. It's kind of higher and kind of smaller up and onto the side of the number. And so this just says the limit as x approaches c or whatever number from the left. And likewise, the right-hand limit would then be a little plus sign up where an exponent might be. And it would say, you would say something like the limit as x approaches c or whatever number from the right. And I didn't give you tables on this page, but you can do them in the margins, and that's fine. But what we want to do, and this may feel for the first couple of examples a little bit like, well, why is this any different than what we've been doing? But there are going to be times when we really only want to focus on one side of the limit, and so I want you to have practiced the left limit, the right limit, and then the fact that the limit in general is composed of the agreement of the left limit and the right limit. So we'll start with this problem and go ahead and type the function x squared minus 3x plus 4 into your calculator, and then create a table. And you remember that your table, we're going to have 6 lines on the table. So I'm going to make my table, and I probably won't have room to write everything, and I'll just 1, 2, 3, 4, 5, 6. So there's 6 spaces there, and we want to look at the function as x approaches the value of 1, positive 1, from the right first, and then from the left, and then just the general limit. So I'm going to start with the limit from the right, and those are going to be the numbers on the right side of the table. And then I'm going to compute the limit as we approach, as x approaches 1 from the left. And so those are going to be the numbers on the left side of the table. And then lastly, we'll talk about the limit in general. So we want to still put positive 1 in the middle of the table. And we're going to start by approaching it from the right. So I'm only going to talk about the numbers on the right. And so my x values, as usual, would start with 1/10 to the right of 1. So positive 1.1, positive 1.01, positive 1.001. Go ahead and plug all that into your calculator, compute those values, pause the video, fill them in, and then come back. And so what I hope that you see is that as x approaches 1 from the right, y approaches 2 from the right. Well, y approaches 2. We don't talk about the y values approaching from the right or the left. So as x approaches 1 from the right, the y values approach 2. And so that's going to be our answer to the limit on the right. Now ignore the limit on the right and look just at what I highlighted in blue, and we're going to approach x from the left. So now this time we're going to do that problem again, but we're going to approach x from the left, or x equals 1 from the left. And so in this case, the numbers in the table are going to be to the left of positive 1, so it's going to be 0.9 and 0.99 and 0.999. And so we're going to have 2.11 and 2.0101 and then 2.001. And again, I hope you see that as x approaches, oh, I didn't turn off the video, did I? I just gave you all those answers without making you work for it. Was thinking about something else. So as you approach as x approaches 1 from the left, the y values also approach 2. And so your limit from the left is the same as your limit from the right. So over here we're going to fill in a 2. And to answer the limit as x approaches a number and you don't have that little plus or minus sign indicating from the right or from the left, then we're just going to say that the limit approaches 1. And the only way for that limit to exist is if both the limit from the right and the limit from the left are the same answer. And so that's going to be the limit equals 2. And so yes, the limit exists. Now we're going to do the same thing for number 6, but this time we have a piecewise function, and we're looking at the first equation for all the values that are less than -2, that means to the left of -2, and the second equation is all the values that are greater than or equal to -2, and so that happens to be all the values that are to the right of -2. And so here we are looking at the limit as x goes to -2 from the right, the limit as x goes to -2 from the left, and the limit as x goes to -2, not from the right or the left, but the limit just in general. And so what I want to do here, be careful of the colors, because the limit from the right is the second equation. And the limit from the left is the first equation. So just make sure you understand which equation you're using for which. Go ahead and set up your table. The number at the middle of the table should be -2. The numbers on the right are, I had to stop and think about that for a second, are the numbers that I'm highlighting in blue, and the numbers that are on the left are the ones that I'm highlighting in green. So I'm going to start with the numbers on the right. Be careful, because 1/10 to the right of -2 is -1.9. And so then you've got -1.99 and -1.999. And then I'm going to ask you to pause the video, go ahead and use your calculator with the second equation and fill in that table, just the values on the right, and then check back for the answers. And so this is what I got for the values on the right, and you can see that as x approaches -2 from the right, y seems to be approaching -4. And so our answer to the limit on the right is going to be -4. Then I'm going to do that whole process again, but this time I'm going to do the numbers approaching -2 from the, as x approaches -2 from the left. And 1/10 to the left of -2 is going to be that -2.1. So we're going to then do -2.01 and -2.001. And so when I go ahead and pause the video, I almost did it again. Go ahead and pause the video, fill in the table, and then come back. And remember that in this case, you're using the first equation for the green. So as x approaches to -2 from the left, we see that the y values approach +3. And so there's no agreement here. So over here, my answer as we approach -2 from the left is going to be +3, but because those two answers are different, then your limit is going to be does not exist. And so let's say that here the limit does not exist, and let's give that a reason. And the reason is that the left limit does not equal the right limit. So number 7 asks you to find the left and right limits as x approaches +1, and then the limit as x approaches +1 of this given function x squared minus 5x plus 4. So if we make our table here, x and f of x, I almost don't have enough space, and so we're approaching +1 here from the left and from the right, and let's do from the right in green, and that's that little plus sign next to the 1, and then from the left in blue, and that's that little minus sign next to the 1. And so as our numbers approach +1 from the right, 1/10 to the right of 1, or 1/10 more than 1 is 1.1. So I'm going to go backwards toward the middle, 1.01 and 1.001. And go ahead and plug those numbers into your calculator. Use the second table set and change independent to ask. And fill in those numbers. Pause the video. Yeah, I forgot that 1 in the last x value, 1.001. And so these are the y values that you should get. And you will see that they get, as you go from the right, as x goes from the right toward +1, the y values approach 0. And so your answer here for the right-hand limit is 0. And now we're going to look for the left-hand limit. So ignore everything on the right there. 1/10 to the left, or 1/10 less than +1 is 0.9. And so we're going to have 0.9, 0.99, and 0.999. Go ahead and pause the video and fill in the rest of the table here. And so here are the y values that you should have gotten. And you will see that as x approaches 1 from the left, the y values also approach 0. And so the left and the right limits are both 0. The left and the right limits are both 0. And since they are both the same, then the limit exists and is equal to that number, 0. So yes, the limit exists. And in number 8, we're going to look at this crazy equation, x squared minus 4x minus 5 over the absolute value of x minus 5. And just to make sure everybody's on the same page, when you type this into your calculator, use the fraction function, the alpha y equals enter, to give yourself a numerator and a denominator. And in order to enter an absolute value into your calculator, press alpha and then window, and then it's number 1. And so for this function, we're going to be looking for the limits x goes to 5 from the right and from the left, and then in general. And just make note that x minus 5 means that at x equals 5, there's either going to be a whole or an asymptote. And so we need to be careful of the values that we're looking at. So let's start with making our table. That's an x. There we go. And then let's again do, the green is approaching from the right, and the blue is approaching from the left. So the green is approaching from the right. That'll be this side of the table. Oh, I didn't put the number on top yet. I'll come back and do that. And the blue is approaching that number from the left. What number, you might say? Well, the number 5. We're approaching it from the left and from the right. So let's start with approaching it from the right. And it's +5, and so we're going to start with 5.1 all the way to the right. And then moving toward the middle, 5.01 and 5.001. And that's how it would be on a number line. So if you go ahead and pause the video and type this all into your calculator. And so these are the numbers that you should have. And you'll see that on the right, as x approaches 5 from the right, y approaches positive 6. And then let's do those same computations as x approaches 5 from the left. And so the numbers for your x values here are going to be 4.9, 4.99, and 4.999. So again, go ahead and pause the video and fill in your table. And so these are the values that you should get, and you will see that as x approaches 5 from the left, the y values approach negative 6. And those two numbers are different. And so over here, because the right limit approaches positive 6 and the left limit approaches negative 6, then the actual limit does not exist. So no. And let's give the reason as here. The left limit does not equal the right limit. Now, the rest of this packet or the rest of this lesson is about continuity. And please remember that when I first started teaching this unit, I said that I kind of gave you a little warning that the concepts of continuity and limits absolutely necessarily overlap, but in such a way that tends to confuse students. And so you need to make sure that when you are answering a question about limits, that you don't answer with a continuity answer, and when you're answering a question about continuity, that you don't answer with a limits answer. Be real careful about that. And the other thing that I want to point out, and this is my fault, so I apologize, I used some wrong vocabulary. So as I go through, and it's the same sentence I copied and pasted into the notes packet several times, starting on this page and going for the next couple of pages. So as I go through, I'm going to change the wording of it, and I will apologize now because I told you to be careful of the wording, and then I messed up the wording. So hopefully that'll help you remember not to mess up the wording. So let's start with repeating what we learned in the previous lesson about the explanation or definition of a continuous function. And I think what I'm going to do is pause my end of the video, write out the definition so that you don't have to watch me writing it. And then when I come back, it'll be written, and you can just pause the video and do what you need to do for writing it. So the graph of a continuous function has no breaks, holes, or gaps. Mind the gap. If you can trace the graph without a pencil, with a pencil, without lifting the pencil, then it's continuous. Otherwise, it's discontinuous. So take a minute, write that down, and then we're going to talk about the continuity test. Now, this is where we're going to start getting into some of the methods that you'll see more and more as you take upper level math classes. And this test has 3 steps, and you're going to need to work through all 3 steps. Even if you know already at the beginning of the first step that the answer is going to be yes or no, you still need to show all 3 steps. It's going to be slightly frustrating for you, or maybe anyway, because you're going to feel like, well, if I can prove in the first step that it's not continuous, why do I need to finish the test? And it's just part of mathematical completeness that you need to show all 3 parts of it. And so there's 3 things, and the first thing is the one that I have reworded each time. So let's say that we're looking at a function and we're focusing on a certain x value. And in this explanation here, we're talking about x equals c. So every time you see a c, that means x equals c, and that's the x value that you're focusing on. And what I had said just a minute ago was that it's number 1 that I have written incorrectly. See if you can catch my word before I show it to you. Instead of saying that f of c exists, it should just be that f of x is defined at c. And then I shouldn't really even have meaning f of x exists. F of x needs to be defined at that x value. That's the first thing you need to make it continuous. And then the second thing that you need to show the continuity test is that the limit of f of x approaches the same value from either side, meaning the right-hand limit and the left-hand limit are equal to each other. And then the third thing that you need to show the continuity test is that your answer for part A and for part B is the same number. You need to show all those 3 things. So, and let me just, well, I think I'll do that at the end. So what I'm going to do is, in the problems in this packet, I'm going to walk you through step 1, step 2, step 3. But on the test, when you take the test, I'm basically going to give you your problems like this. Here's the box that your problem's in, and I'm going to say, is f of x equals blah, blah, blah with an x in it, blah, 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 continuous at x equals, let's say, -8, question mark. And then there's going to be all this blank space. You have to then go say, okay, step 1, blah, 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 f of -8 equals yada, yada, yada. Number 2, the limit as x approaches -8 is yada, yada, yada. And number 3, my answer to part 1, does or does not equal the limit as x approaches -8, yada, yada, yada. And then yes or no, it's continuous or not continuous. You're going to need to write all that stuff in red. The stuff in purple is all I'm going to give you as the question. So yes, you need to memorize the continuity test, not word for word, but just the process of it. So let me walk you through, and literally most of the rest of this notes packet is going to be just working through the continuity test and seeing the different ways that it can vary. So I wanted to start out with a fairly straightforward example here. So the answer is going to be yes. I'll tell you that at the beginning of the problem and give you that as a hint. That kind of ended abruptly because there was a big noise in the street, and then, yeah, I just needed to re-record some of this. So here we go. So I already told you that this is going to be continuous. My apologies if I'm repeating myself. And so you want to do 3 different steps here. The first thing you want to do is change Miss Applebacher's wording. This should not say, does f of 2 exist? What it should say here is f of 2 defined? And so all you need to do is just decide, first of all, if there's no restrictions on the domain, then every x value is defined. So this is just a quadratic graph. There's no square root, there's no denominator, there's no logarithm. Therefore, it's defined over a domain of all real numbers. So yes, f of 2 is defined, but then what you want to do is find f of 2. So literally all you do is just type in to your calculator 2 times 2 to the second power minus 3 times 2 minus 1, and you should get that f of 2 is equal to positive 1. And so your answer here is yes, it's defined. F of 2 equals positive 1. Then your next question is, does the limit as x approaches 2 exist? Remember that functions are defined or not defined. Limits exist or don't exist. And that noise you hear in the background is my friend's dog that I'm dog sitting, and he's decided that his bed needs to be scratched. So anyway, sorry. So anyway, the limit is just the normal limit process that we've been doing. We're approaching, x value is approaching 2 from the left and from the right. And so I'm going to fill in those numbers starting at 1.9 here, 1.9, 1.99. I think he has not yet finished. I thought he was done. And then over here, 2.1, 2.01. When I said there was a noise in the street, then the dogs reacted to the noise in the street because there's a couple dogs here, but they're cute, so I tolerate it. So this is what your table should look like. And he's still working on his bed because the noise in the street then disrupted his sleep, and then it's middle of the afternoon, but he needs to remake his bed. So go ahead and pause the video and fill in the rest of the table, and I'm going to make sure that his bed is okay for him, and then we won't have any more noise in the background. Yeah, so he finished with his bed and then got off the bed and went and took a nap across the room next to his brother. Craziness. So at least they're asleep now. So the y values, you can see, as x approaches 2 from the left, the y values approach +1, and as x approaches 2 from the right, the y values also approach +1. And so we're going to say, yes, the limit exists. So yes, the limit exists. Yes to this question. And then the other thing that you need to just kind of make a note of is the limit as x approaches 2 of the function equals 1. And then last but not least, what you have to do here then is say, okay, if the first step of the continuity test is to see if the function is defined and what's the function value, and if the second step of the continuity test is to see if the limit exists and what is the limit equal, then the third step of the continuity test says, if both of those answers are yes, are the answers equal to each other? Does the value of f of 2, the function at 2, equal the value of the limit? And so we said that the value of the function f of 2 is 1, and the value of the limit is 1, and so 1 equals 1, and so your answer here is also yes, and the function is continuous. And that's the basic continuity test. So take a look at this next function, and notice that the rational functions could potentially have wholes or asymptotes based on what would make the denominator 0. And you're not asked to compute that in this case. All you need to do is work through that 3 steps of the continuity test. You need to decide if the function is defined at x equals -5. You need to decide if the limit at as x approaches -5 exists, and then you need to look and see if both of those are yes, then do the values equal each other. And this is going to be kind of like how you're tested, where I ask you that question and then give you a big blank space, and you're going to need to fill those steps here. So your first step is f of -5 defined. Now, you could do this 2 ways. You could enter the function into your y equals screen and then look at -5 on the table and see if it gives you a value for -5. Or if you wanted to, you could just do something like this and say, f of -5 would equal, and then just substitute -5 in a -5 squared minus 3 times -5 all over, and then -5 squared again, plus 2 times -5 minus 15, and you can compute it that way. Either way you do that, whether you look at the graph, whether you look at the table that generates the graph, or whether you compute the value of the function this way, what you'll find is that -5 makes the denominator 0, and so you'll say, no, it's not defined. F of -5 is undefined. Now, having said that, you know it's not continuous. You already know it's not continuous, because if your answer is no to either of the first two questions, then it's automatically not continuous. But what I want you to do is actually show all 3 steps of the continuity test, so that you can see how the process works and how the completion of the mathematical verification works. So I'm going to go ahead and do the second test, which is the limit. And so I'm going to say number 2 does, now watch how we write this, the limit as x goes to -5 of f of x exist. And then you're going to draw your table and fill in your table and do all the things that we've been doing for limits. And so that's going to be f and x and f of x. And I want -5 to be the number in the middle here. And so we're going to have x approach -5 from the left and from the right. And so remember that when you are filling in a table for values of a negative number, that the numbers feel like they're going to be the reverse. And so this is going to be -5.1, -5.01, and -5.001. And then from the right, it's going to be -4.9, -4.99, and -4.999. And then go ahead and pause the video and fill in the y values on this table. So these should be the y values that you see. And again, use this kind of as a review of what you understand about limits. On the left, you should see that as x approaches -5 from the left, you should see that the y values go to positive infinity. And as the x values approach -5 from the right, you should see that the y values approach negative infinity. And the other thing that I want to, well, 2 things I want to point out. First of all, the limit doesn't exist because you've got infinity somehow involved in the answer to the limit, and therefore that's a limit that doesn't exist. And the second comment is that the 2 infinities are the opposite sign. So one's positive infinity, one's negative infinity. Remember that when your answer to a limit problem is infinity, x goes to a number, generates a limit of infinity, that means that it's a vertical asymptote. And that was from the front page of the same packet. So your answer to the question in number 2 is, does the limit exist? Well, no, the limit doesn't exist. D and E, and it's does not converge to a value. let's just write does not converge. Okay. So now you've got your first two steps. Both of them alone would be enough to disprove continuity or to show that there's a discontinuity at -5. And again, I'm going to say, remember that I want you to write out all three steps. So basically, then what you want to do for number 3 is say f of -5 does not equal the limit as x goes to -5 of f of x, and therefore discontinuous. Now, I'm not going to give you 17 problems like this. I feel like each one continuity test problem is like 3 problems. So if I normally give you a certain amount of problems on average, I divide that by 3, that's how many continuity test problems I would give you. But this is a very typical upper level math proof, so to speak. Now, what I want to talk about is the different types of discontinuities. Because when I ask you to do the continuity test, or when I ask you about a discontinuity, I'm going to say, if it's discontinuous, what type of discontinuity is it? And so in this first one, removable discontinuity, basically what's happening is that the function would be continuous if it weren't for just this one little space right here, if it weren't for that. And to be more mathematical about it, the limit going from the left and from the right both go to the same number, but that the function is not equal. The function of, or f of that number, is not the same as what the limit is. So here, what might have been a more accurate picture for the type of discontinuity called removable continuity might have been more accurate if I had done this. If I had said, look, there's 2 possible scenarios with removable discontinuity. You could either have a graph that looks something like this, where the function has a hole and it's completely undefined at whatever this function value is, or if you had a situation like this, approximately the same graph here, and a hole still there, but that the function has, that just isn't neat enough for me, but the function, I made it worse. The function has a point defined at a different place. So either the function is undefined at C, or the value of the function at C is different than the limit of the function at C. Both of those are what would look like a removable discontinuity. Do you see that what's given right here is more like the second case? Because the function is defined at that x value, it just isn't the same as what the limit would be at that x value. That's a removable discontinuity. The second kind of discontinuity that you'll need to recognize, I think, is a little bit more obvious, and that's called an infinite discontinuity, and it happens when you have infinity either on the left or on the right, or both, positive or negative infinity, and that causes you to have to pick up your pencil, so to speak, or when it causes the limit not to exist, then that will trigger an infinite discontinuity. The third type of discontinuity is when the limit from the left goes to one value and the limit from the right goes to a different value, and those two values are not the same, and that's called a jump discontinuity. By the way, this point down here, this little x value, doesn't matter. That doesn't have absolutely nothing to do with the jump discontinuity, because remember that we're only looking immediately to the left and immediately to the right of the x value and not exactly at the x value. Either way, you're going to need to pick up your pencil in order to keep drawing. And the fourth type of discontinuity, which I'm barely going to touch on, and don't worry about if you don't quite follow what's happening. You see the oscillation here, and so that's your first clue that I'm not going to do a lot with it, because I told you that I wasn't going to do things with oscillations. But an essential discontinuity doesn't have a limit on either the left or the right, one or the other. So a better example might have been to give you a square root function. So a square root function, let's say in this graph, there's only a limit on the right. So the limit as x goes to, let's call this 2, from the right exists, but the limit here, the limit here as x goes to 2 from the left does not exist. And so if one of those two limits is missing, if either the left limit or the right limit doesn't exist, or if the function isn't defined to one side or the other of the point in question, the x value in question, then that's called an essential discontinuity. And in this crazy picture that I gave you here, if you're looking at x sub 0, the limit on the right goes to infinity, therefore the limit on the right doesn't exist. The limit on the left is this oscillation that we talked about, and therefore the limit on the left doesn't exist. Although you can see pieces of the function on both sides, one or the other or both of them has some issue with the limit, and therefore it's discontinuous. So you're going to need to remember those 4 types of discontinuity. Please don't change the names of them. I know that some of my students have in the past gotten creative with trying to rename these discontinuities, but this is it. Removable discontinuity, infinite discontinuity, jump discontinuity, and essential discontinuity. So let's do the continuity test again with this function here, and add that last question. What type of discontinuity are we talking about? And again, my apologies for having the wrong wording in the first part. This first question should say, is f of -3 defined? Now, be careful when you are checking to see if, when you're checking this first step of the continuity test to see if a function is defined, if it's a piecewise function. Do you see that the -3 is defined in the first equation because of that equal sign? It is not defined by the second equation. And so if I want to check and see if this function is defined, I am going to substitute f of -3 into the first equation, which is 2 minus -3. And when you type something like that into your calculator, don't try to be all fancy and say, I know how to subtract a negative, because if you do it wrong, you get the wrong answer, and then that's going to mess up this whole problem. Just type the whole thing into your calculator, and you should get +5. And so your answer is yes, the function is defined, and f of -3 equals 5. There's the first answer to the first question. So the second question then is, does the limit as x goes to -3 exist? And so we're going to compute the limit of f of -3. And so here, if I am going to, or if I am letting my x values go to -3, I want to approach -3 from the left and approach -3 from the right. And so in my table, remember the negative numbers are tricky, so that's going to be -3.1, -3.01, and -3.001. And from the right, that's going to be -2.9, -2.99, and -2.999. Go ahead and pause the video. Remember that your first equation, the first equation here, is going to give you the values on the left, because those are the ones that are less than -3. And the second equation is going to give you the values on the right, because those are the values that are greater than -3. So pause the video and fill in the table, and then come back to check your answers. So here are the y values that you should be getting. As x approaches -3 from the left, you should see that the limit, or the y values, are approaching +5. And as x approaches -3 from the right, your y values are approaching -11. And because those two numbers are different, then no, the limit does not exist. No, the limit does not exist, because the left limit doesn't equal the right limit. I want to kind of squeeze that in there. Left limit does not equal the right limit. Now, the last question then is, does the value of the function at -3 equal the limit of the function at -3? And clearly it doesn't, because the limit doesn't exist. So we're basically saying no, the function's not continuous, or it's discontinuous at -3 because the limit doesn't exist. But when I ask what type of discontinuity, the fact that you have the left limit not equal to the right limit automatically says that your graph is going to +5 on the left and, what did we say, -11 on the right, and therefore your limits on the left and the right are different. And so that's going to be a jump discontinuity. So it's going to be jump discontinuity. So in number 12, we're talking about this function x plus 3 over x squared minus 9. And we're checking to see if it's continuous at x equals 3. And so the first thing that we're going to do is fix Miss Applebacher's mistake and say, is f of 3 defined? Question mark. So, is f of 3 defined? And in order to answer that question, we're going to substitute the 3 for the x's. So that'll be 3 plus 3 over 3 squared minus 9. And we see that that makes the denominator 0. So your answer to this question number 1 is no. And again, I'll say, I understand that you know at this point that it's discontinuous, but I want you to continue the process so that you show the answers to all 3 steps. So in this next step, you want to ask if the limit exists. And so we are looking at the limit as x approaches 3. And so 3 goes in the middle of my table, and we're going to have the x values approach 3 from the right and from the left. On the left, the x values start at 2.9, 2.99, and 2.999. And then on the right, from all the way to the right is 3.1, and then going backward toward the 3 is 3.01 and 3.001. Go ahead and pause the video, fill in the table, and come back when you're done. So these are the y values that you should have gotten, and remember that when the numbers get real big like that, that means that the limit is going to infinity. So here on the left, as you approach, as the x values approach 3 from the left, the limit approaches negative infinity, and as the x values approach positive 3 from the right, the y values approach positive infinity, and that indicates that there's an asymptote at x equals 3. And so here for step 2, does the limit exist? No, the limit does not exist. And that's going to be because it does not converge. Goes to infinity. Well, the function isn't defined at 3. The limit doesn't exist as x goes to 3, and the answer to that is no. It's not continuous. What type of discontinuity? It's going to be an infinite discontinuity. I'm so sorry. I really meant to make this video less than an hour and a half, and here it is, almost an hour and a half, and I've still got a page to go. And I don't want to rush through this, but you know that with these videos, you can always just fast forward to zoom out and look at the answers, and if you are understanding, you don't really need to listen to me talk through all of the minutiae of each problem. So anyway, here we have, and again, you're going to need to correct Miss Applebacher's math mistakes here. Is f of 2 defined? Or you can say, is f of x defined at x equals 2? Either way, I wrote it wrong. So here is f of 2 defined, and you are going to, well, you can tell just by looking at it that 2 minus 2 in the denominator is going to make it undefined. But let's just, I'm going to show the substitution because I think that helps me be complete. So 2 squared minus 4 all over 2 minus 2. And so my answer here is going to be no. And that's either going to be a whole or an asymptote. We don't know yet, unless you've graphed it and looked at it, and then you have a feel for whether it's going to be a whole or an asymptote. But let's keep going here with the question about the limit. So we're doing the limit as x approaches 2, and I gave you a table to put all of that in. So as x values approach 2 from the left and from the right, the y values or the x values that we're going to use here are 1.9, 1.99, and 1.999. That's from the left. Did I say the right? And then as the x values approach 2 from the right, it's going to be 2.1, 2.01, and 2.001. And if you weren't in class and you're watching the videos and you're finding yourself wondering if they have to be in that order, you've got the same numbers but you've got them in a different order, I would say, yeah, you pretty much want to put them in this order, because this is the order that they would appear if you were putting them on a number line. So anyway, go ahead and pause the video and come back when you have your table filled in, and we'll continue from there. So you filled in your table and you find that the values as x goes to 2 on the left, your y values go to 4. And as x approaches 2 on the right, your y values also go to 4. So your limit here is 4. So the limit exists and it equals 4. Yes. And the limit as x goes to 2 is of f of x is equal to 4. But because f of 2 doesn't exist, then f of 2 does not equal the limit as x goes to 2, and therefore the whole thing is discontinuous. And in this case, the limit exists, but there's no value of the limit or of the function at that x value. So immediately to the right, immediately to the left, infinitely close at 1.999, at 2.001, that function exists except for exactly at x equals 2, and that is that removable discontinuity. So what type of discontinuity? It's removable. Here in number 14 is f of -3 defined. And so we're going to substitute -3 into the function. So f of -3 would be the square root of -3 plus 3, and then outside the square root -2, and that whole deal is equal to -2. So your answer here is yes, it's defined, and it equals -2. Now we're going to compute the limit as x approaches -3. So we want x to approach -3 from the left and from the right. Remember that with the negative numbers, filling in the limits, x values, just don't get yourself confused here. This is going to be your -3.1 and -3.01 and -3.001, and then filling in your x values from the right is going to be -2.9 and -2.99 and -2.999. So go ahead and pause the video and finish filling in the table and come back in a minute and check your answers. Now, any number that's less than or to the left of -3 in this case, all of these x values are undefined. The function is undefined because that would be taking the square root of a negative, which we know that we can't do. So the function is undefined to the left of -3, but to the right of -3, the limit clearly goes to -2. So as x approaches -3 from the right, the limit goes to -2. Well, since the left-hand limit does not equal the right-hand limit, then the limit does not exist. Ooh. DNE, doesn't matter if DNE is capitalized or not. I know I've been inconsistent. And you can say something like, here the left limit does not equal the right limit. And therefore, the question, does the value of the function equal the value of the limit? The answer is no there as well. It's discontinuous. And this type of discontinuity, I'm not going to put on your test, but it's the one where one side of the function just doesn't exist. There's nothing going on, or the limit doesn't exist on one side of the function, and so we're going to call this an essential discontinuity. I'm not testing you on that one. And then example 15, we're looking at this function and we're checking to see if it's continuous at x equals 4. And so the first thing that I want to do is substitute. First thing we're going to do is fix Miss Applebacher's math mistakes. Is f of 4 defined? Now we're going to say, well, I don't know. Let's compute f of 4, substitute the 4 into the equation for all those x values. So it would be here 4 squared minus 3 times 4 minus 4. Plug that whole thing into your calculator and you are going to see that it's undefined. So your answer here is going to be no. It's not defined at x equals 4. And then we want to see if the limit exists as x approaches 4. And so let's fill in the table here. As x approaches 4 from the left and from the right. On the left, we want to use the x values 3.9, 3.99, and 3.999. And then over here, 4.01, that's not right, 4.1, 4.01, and 4.001. So go ahead and pause the video, plug all these numbers into your calculator and compute your y values, and then come back. So 2 things you should notice right away is that we've got some infinities involved in our answers, and that what's happening on the left of x approaching 4 isn't the same as what's happening on the right of x approaching 4. So on the left, as x approaches 4 on the left, our y values approach negative infinity. As x approaches 4 on the right, our y values approach positive infinity. And so no, the limit doesn't exist, and it doesn't converge to a value. Well, since both of those answers are no, your answer to the third part is also going to be no. It's discontinuous, and it's an infinite discontinuity. Last but not least, and we'll do more of this in class on the review day, but I want you to take a look at this graph here. There's several things going on here. I see a horizontal asymptote. I see a vertical asymptote. I see a jump discontinuity. I see a removable discontinuity. I see a place where the function is defined at a different place than the limit. I see a place that has a different limit on the left and on the right. And then I'm going to ask you a bunch of questions about function values and about limits, general limits, limits that involve infinity, limits, right-hand limits and left-hand limits. And you're not given any kind of equation, and so all you can do is observe the graph and give your answers based on what you observe in the graph. And I want to walk through these questions in order because I ask them in a specific order to get you to think through the answers in a specific way. So I'll start with letter A, which asks for f of 4, and that just means when x is 4, what is y? And in this case, your answer is going to be 0. And part B asks you for to find f of -2. So again, you want to look and see where where x is -2, and that's where I see something that looks an awful lot like a vertical asymptote. And so just to help myself to answer some of the other questions, I'm going to draw an asymptote there, and if that's not an asymptote, then nothing is. And so remember, what is the answer when there's no, when the function doesn't have a value at that given x value or doesn't have a y value at that given x value? Make sure that you put undefined. And don't get confused between undefined and does not exist. So the value of the function at x equals -2 is undefined. Then it asks, what's the value of the function at 0? Well, where x equals 0 is right here, and you have an open circle and you have a closed circle, and remember that the closed circle is going to be the true value of the function. And so your answer for letter C is going to be -1. Then in letter D, you want to find the value of the function at 2. And so here's the function at x equals 2, and that answer is also going to be the y value is 2. And then the what I think is the tricky one is, what is the value of the function when x equals 3? What is f of 3? Well, you have here a hole, but you have here a point, and so the value of the function at 3 is going to equal +3. The y value there of the point near the top is +3. The next two questions ask you to look at the end behavior as x goes to positive infinity and as x goes to negative infinity. So for letter F, as x goes to positive infinity, I want to look at the right end of the graph, and it sure looks like that graph is going down. And so my answer for letter F is going to be negative infinity. Letter G asks me to look at the end behavior as x goes to negative infinity, and that sure looks to me like a horizontal asymptote. In fact, like I said, I'm going to draw in that asymptote so that you can see it. Now remember that a horizontal asymptote is about end behavior, and it doesn't have to be the same end behavior at both ends. So we're only going to talk about that horizontal asymptote in regards to the left end behavior, which is when x is approaching negative infinity. And so we want that value of the limit to be 1 then, because the horizontal asymptote appears to be 1. Now in letters H and J and K, we're going to look at the limit as x goes to 0 from the left and from the right, and then take those two answers and help us to answer the limit as x goes to 0 in general. And I think the next thing that I'm going to do is actually just erase the scribbles that I put on the x equals 0 so far. And I am going to start to color code just a little bit here, that if I'm talking about x going to 0 from the right, that's this part of the graph. And so the limit as x approaches 0 from the right goes to -1. me change colors now, because as we approach, I'm running out of colors. Let's do blue. As we approach 0 from the left, as we approach x equals 0 from the left, that's going to be here. And whether there's an x value there, exactly there or not, it doesn't matter, because all we care about is immediately to the left of x equals 0, not right at x equals 0. And that value, let's just make up a number. How about 1.2 or 1.3 would be sufficient? And so my answer here for the limit as x goes to 0 from the left is going to be positive, let's say 1.2. Well, the limit as x goes to 0 in general, that would be k, as x goes to 0 in general, would require that the limit on the left and the limit on the right have the same answer. And since the limit on the right is -1 and the limit on the left is 1.2, then the limit as x goes to 0 does not exist, because it's different on the left from the right. And let's just say here that the left limit does not equal the right limit. The next two questions just ask for a general limit, not specifically right or left. And again, I'm going to go back and erase some of my scribbles. So for 2 and for 3. So number 2 asks about the limit as x goes to 2. And you should see that as x goes to 2 from the left, we're going to positive 2. And as x goes to 2 from the right, we're also going to the y value of 2. And so your answer for the limit as x goes to 2 is 2. And then for letter N, we're looking at the limit as x goes to 3. And so remember that the limit is not about the actual point value. No. It is about what's happening immediately to the left and immediately to the right of that x value. So if this is x equals 3, as x approaches 3 from the left, as x approaches 3 from the right, the y value approaches 1. Has nothing to do with this up here at all. And so your answer for this last one, the limit as x goes to 3, is positive 1.